Okay, so uh, in the last class, I proved this representative theorem, this very general statement which says that as long as you have a PDS kernel and H is the corresponding reproducing kernel Hilbert space, any optimization problem which can be expressed in the following form, which is monotonic, where the objective function is a monotonically increasing function of the norm of H plus some loss function, any arbitrary loss function of the evaluations of H on n data points. This always has a solution as a linear combination of the phi xi's, right? And we use this in particular to show that so firstly, it means that for any kernel SVM problem, the optimizing solution is always a linear combination of the support vectors in the Hilbert space. But then we also kind of use this. I didn't say how we use it, but it can be used to design a computationally efficient algorithm to learn a kernel SVM. Right, so you can design stochastic gradient descent algorithms to find your kernel SVM, and this can be done fairly efficiently. So in this class, I want to discuss two different applications, other applications than what we've seen in class. Previously, we've essentially only focused on binary classification. So today I want to very briefly talk about regression and PCA. Right. So what is the specific problem we are interested in? Right. So first, let's look at regression. So let's recall the linear regression problem. So in general, what does regression in RD or linear regression in RD look like? You basically want to find the minimizing A that essentially minimizes your empirical risk, and typically for linear regression, the empirical risk is the squared error risk. So you're given a bunch of data points, x1 through xn, which are all vectors in RD, and along with this, you're given the corresponding labels y1 through yn, which are all elements in R in general. Right? And in this case, what we want to know is, well, you want to minimize the squared error risk or the squared error loss. So typically you want to minimize 1 by n summation I equal to 1 to n of yi hat minus yi the whole squared plus perhaps a regularization term. Right, so we're dealing with what is called ridge regression. So there is a regularization term of the form lambda by 2 norm a square. And what is y hat? This is going to be equal to n, simply A transpose xi. Right, so your predictor is just a linear predictor. Plus lambda by 2. So we're just trying to find that hyperplane that best fits the data points that we see. Right. So this is just standard linear regression, and I'm sorry. Which one? So this the target variable is assumed to be 1D in this case. But more generally, you can just have the squared norm instead of just the square, right? So, so this is linear regression, and as you've seen previously, the solution can be obtained fairly simply. It's just it can be, you can solve this or find A by just by solving a set of linear equations, right? So that can be implemented computationally efficiently. Now, what if we're interested in non-linear regression in RD? So more generally, uh, we have some feature mapping f from RD to some Hilbert space H, and what we want to do is minimize f in H of summation I equal to 1 to n. Now our prediction is no longer A transpose xi. This is just going to be some f of xi rk to r, and this f comes from some Hilbert space of functions. All right, so your hypothesis class in some sense is just a Hilbert space of functions instead of taking just a set of all linear functions. Whole square plus right. I'll tweak the objective function a little bit. Instead of having this 1 by n, I'll just replace it with a half. It's just a rescaling, and it doesn't really change anything, because I can always choose this lambda appropriately based on n. Right, so this is the non-linear regression problem that we're trying to solve. And the question is, can this be implemented efficiently? We'll see why, because that simplifies things. In fact, H is going to be a reproducing kernel Hilbert space. If this is some arbitrary class of functions, then we don't have an efficient way of finding this minimum, right? Because it can be fairly general. Now let's begin with this. By what does the representative theorem tell us? What is f of xi? Sure. So in fact, let's take another step back. Since f comes from a reproducing kernel Hilbert space, what is f of xi by definition of the RKHS? Sorry? Correct. It's basically an inner product between f and a kernel, right? This half summation I equal to 1 to n of inner product between f and p xi minus yi whole square plus lambda by 2 norm square. The representative theorem anyway tells us that the solution is going to be a linear combination of the phi xi's. The optimizing f is going to be a linear combination of phi xi's, but then we still don't have an efficient way of finding that linear combination. So the whole point is to try to efficiently find this linear combination. Okay, so this is an inner product between f and phi. Is there some way of simplifying this. Now, again, by the representative theorem, f is going to be a linear combination of the phi xi's, right? So suppose f star is sum j equal to 1 to n alpha j phi xj, right? Let's see what happens when we replace this f by f star. Simply get half summation I equal to 1 to n of inner product between summation j equal to 1 to n alpha j phi xj with phi xi minus yi the whole square plus lambda by 2 times the norm of correct. But what can I say about this inner product? I can expand this out, right? Just by using the linearity property of the inner product. This half summation I equal to 1 to n summation j equal to 1 to n alpha j inner product between phi xj and phi xi minus yi the whole square plus lambda by 2. Again, I can write this as summation I equal to 1 to n summation j equal to 1 to n alpha I alpha j inner product between, because I simply write this as the inner product between this vector at itself phi xi phi xj. But what is the inner product between phi xi and phi xj equal to? K of xi xj. All right. Now let me just stack all of the alpha i's as a vector. So alpha I is simply this vector alpha 1 through alpha n, right? What does this look like? Yep, it's the dot product between what? Correct. But can you write it in the form of matrix multiplication, matrix vector multiplication? Correct. So in other words, it's going to be the product of the ith row of the matrix K along with the vector R, right? So this is nothing but half summation I equal to 1 to n of, I take the ith row times alpha minus yi the whole square plus lambda by 2. What does this look like? Yep, so it's just alpha transpose the kernel matrix K times alpha, right? And what is this exactly equal to? Let's assume that I stack the yi's as a big vector. Yeah, K alpha. Correct. So it's K alpha minus y 2 norm squared. So it is just half of the 2 norm squared of K alpha minus y squared plus lambda by 2 times alpha transpose K alpha. Right. So in other words, solving for this problem, where we had to find this solution in the Hilbert space, is equivalent to finding that alpha, that vector alpha, that minimizes this particular quantity. So the problem simply reduces to finding argmin over alpha of half K alpha minus y squared, the 2 norm squared, plus lambda by 2 alpha transpose K alpha. How do we find the solution? You take the gradient and set it to be equal to 0. What do you get? Firstly, are you convinced that this is a convex optimization problem? Why? That's a quadratic term. Okay, is every quadratic optimization problem a convex optimization problem?
Yes, yes.
Correct. So what properties are using? This is anyway a convex optimization problem. It's a norm squared. The second one, the gram matrix, is PSD. So we're making use of that fact here. Right. Okay, so what is this? What is the gradient equal to? It's K alpha minus y plus lambda times, right? Sorry, K plus K transpose. But what is K plus K transpose? It's 2K. This is equal to 0, or it's equivalent to saying that K plus yeah, K into, let me just check if I missed something. Where? The derivative of norm square. What should it be? It should be K transpose. Well, let's just expand it out. That's easier. Okay, alpha minus y transpose K alpha minus y is equal to alpha transpose K square alpha minus 2 alpha transpose Ky plus y transpose, right? I'm just using the fact that K transpose is equal to K. So this, when you take the derivative of G or the gradient of G with respect to alpha, the same as saying that K square alpha minus alpha, sorry, K times Y. Any problem? Ky plus lambda K alpha. This should be equal to 0. So K times K plus lambda I times alpha should be equal to K times Y. If K and K plus lambda I are invertible, then I can just take the inverse on both sides and directly find the solution. But in any case, solving for alpha is the same as solving a set of linear equations. There may or may not be a unique solution to this, right, depending on whether these matrices are invertible or not. But then this means that everything, including polynomial regression, can be solved just by a system of linear equations. Because if we are fixing the degree of the polynomial, then that amounts to just doing kernel ridge regression with a polynomial kernel. And for irrespective of what the kernel is, everything can just be solved using this matrix, the set of linear equations that only depends on the kernel matrix. Right? So that's a simple application of the representative theorem for a problem in learning. Here's another, which is PCA. Yeah, sorry. Hilbert space. Yes, RKHS. Yes. Well, again, typically you don't start with the reproducing kernel Hilbert space. You start with the kernel itself. So once you take a kernel that defines an RKHS and that defines hypothesis class. Yeah, when designing the algorithm, you typically don't start with H. You start with K. In certain cases, you know what H it corresponds to. For example, polynomial kernel. But in general, you don't really care about what the H is. So H serves more as a way of theoretically explaining how you're deriving the algorithm, right? Or an interpretation. Yeah. But when you're actually trying to solve the problem, when you're trying to actually design an algorithm, you just start with the kernel. Okay. All right. So what is PCA? PCA is essentially a means for dimensionality reduction. You have a bunch of vectors, a bunch of data points, x1 through xn, that all lie in some space. Let's say that each xi is in Rd. Let me collect all of these vectors as columns of a matrix, which I call the data matrix. The goal of standard PCA is to, you can interpret it in two ways. One is to reduce the dimensionality of these vectors, that is, map each xi into a lower dimensional subspace. Xi to a lower dimensional subspace, maybe a k dimensional subspace where k is something much smaller than d. Another interpretation of this is that you know that there is not a lot of variation in the vectors. In fact, it could be that most of the information lies in some k dimensional subspace of Rd, and essentially you want to find out in which directions you have most of the variation in the data. Right? That's another interpretation of the problem itself. One assumption that we will make is that the data doesn't have any bias, in the sense that summation I equal to 1 to n xi, this is equal to the 0 vector. So this is required to interpret this as, in the sense that a lot of the variation is contained in some k dimensional subspace of Rd. Yeah, we just center it up. Correct, that's true. Right. So what does it mean to map xi to a lower dimensional subspace? We just want to find a projection of x onto some lower dimensional subspace. So find some projection matrix P. So you can think of this as a d by d matrix, but this essentially has rank only k, and this is an orthogonal projection onto some k dimensional subspace. In other words, I can write P in the form U transpose, where U is just a D by K matrix with orthogonal columns. Or with orthonormal columns. So let's call the set of all such matrices Pk, P subscript k. So now, of course, there could be multiple orthogonal projections. What does it mean to find the best orthogonal projection? One way of doing this is essentially to minimize the squared error loss. Right? So you have these n data points. I want to find that projection such that the squared error loss between p times xi and xi, the squared error loss is as small as possible. That essentially amounts to minimizing the Frobenius norm between p times x, or the error between p times x and x. Right? Question? Right? So suppose that this is indeed our objective, that is to find that projection matrix which minimizes this objective function. Okay, so this can be written as R min over U, all orthonormal D by K matrices U, of U transpose X minus X Frobenius norm square. What do we know about the columns of U? Yeah? Can you speak up? There'll be unit norm, I agree, but for this particular problem, for the PCA problem, what does the UI? Which item? They are eigenvectors, I agree, but which eigenvectors? Correct, but which eigenvectors? I mean, there are k, right?
The one corresponding to the k largest eigenvector.
Yeah, so these u1 through uk are the eigenvectors that correspond to the k largest eigenvalues. Of xx transpose, I guess 1 by n. It doesn't matter whether I take 1 by n or not, because the eigenvectors are all orthogonal. And why is that the case? Correct. So you just take u transpose x minus x Frobenius norm squared. This is just trace of this matrix times, or the transpose of this matrix times the matrix itself. So this is u transpose x minus x transpose times u transpose x minus x. This is the trace of this transpose times this matrix. So that is x transpose u transpose u transpose x plus this transpose this x transpose x minus 2 times x transpose following. So x transpose u transpose x, right? This is equal to what is u transpose u equal to? The identity, because it has orthonormal columns. So this u transpose u, this is an identity matrix. So I have x transpose u transpose x minus 2 times x transpose u transpose x. This is just trace of x transpose x minus x transpose u transpose x, right? Now what is the goal? The goal is to find that u which minimizes this particular quantity, right? Out of these two, now again it's a trace of a sum of matrices that's equal to the sum of the trace of these two matrices. This is just trace of x transpose x minus the trace of x transpose u transpose x. So minimizing this Frobenius norm is the same as maximizing this particular trace. The trace of x transpose u transpose x. right? But that's also the same as maximizing the trace of U transpose X, X transpose U. Because trace of A times B is a trace of B times, right? Okay. Now this is the same as the trace happens to be equal to summation I equal to 1 to K. If I look at just the diagonal entries, this just happens to be UI transpose X, X transpose UI. All right. And why is this maximized when you take the UIs to be the K largest eigenvalues? I mean, eigenvectors corresponding to the K largest eigenvalues.
That's for the X.
Okay.
The largest singular values of that by norm.
Fine. So suppose that K is equal to 1, right? We're only looking at UIs with unit norm. So X transpose or U transpose AU is maximum when you take U to be the largest, the eigenvector corresponding to the largest eigenvalue. But why does it in general have to hold for K vectors? Or how do you prove that particular result? It's largest. The UIs are they're orthonormal, right? They all have unit norm. They're all linearly independent, and they're orthogonal to each other. What kind of a matrix is XX transpose? It's symmetric, sure. What else? Is it PSD? But positive definite, not sure. Depends on what matrix X is. X is an arbitrary data matrix, remember that, right? Is it PSD? Okay, it is a dot product. It's a more fundamental reason. It is PSD. What is U transpose this matrix times U? Yeah. So it's U transpose X, X transpose U. This is just the L2 norm squared of X times X transpose U. Right? and that is guaranteed to be greater than or equal to 0 for all the. So XX transpose is a symmetric positive semi-definite matrix. What can you say about what results do you know about symmetric PSD matrices that can be used? Okay, the eigenvectors are orthogonal, correct? Is there a canonical decomposition of symmetric PSD matrices? Yep, correct. So in other words, you can write it in the following slightly more convenient form, which is x transpose is summation I equal to 1 to so what are the dimensions of XX transpose? Going to be d cross d, so it should have d eigenvalues. So this is going to be summation I equal to 1 to d lambda I some let me call this ei transpose, where ei is the eigenvector corresponding to lambda I. It's PSD, so all of the lambda i's are guaranteed to be real and non-negative. Right? We just leave this as a homework. Using this, show that this quantity is maximized when the u1 through uk they have to lie within the subspace spanned by the k largest eigenvectors. Which one will be zero otherwise? Oh, sorry, what will be zero otherwise? If what is not satisfied, so the solution will lie in the span of the eigenvectors of XX transpose. Saying the solution will lie in the span of the eigenvectors corresponding to the k largest eigenvalues. That's a subspace. The k, whatever, the d eigenvectors will span all of Rd. They form a basis for Rd. Right? Okay, so then therefore the PCA solution is you just find u to correspond to the k largest, the eigenvectors the column vectors can be taken, the columns can be taken as eigenvectors of corresponding to k largest eigenvalues of XX transpose.
That's an eigenvector in the above expression, the max expression.
Yep.
That's an eigenvector.
Okay.
So, of XX transpose.
Okay.
So then XX transpose UI is from lambda UI.
Yes.
And that's lambda I mod UI square, which is anyway just summation lambda.
Correct.
So it's a flat sum. Because when you're adding the highest k lambda.
You're adding the highest k
UI
lambda.
must be out.
But why you can choose a UI that is not necessarily an eigenvector, right? So why does that achieve the maximum? Because you can be anything. No, you're not just looking at, you're not just maximizing over the D eigenvectors, right? You're maximizing over all of our D. Again, it's not very complicated. It's just along similar lines. Just have to be a little careful. All right, so that's standard PCA, right? But what do we do if we want to solve the following kernel PCA problem? Now, unlike standard PCA, where the assumption is that a lot of the information is contained, or a lot of the variation in the data is contained within a k-dimensional subspace, in this case, it's going to be in some k-dimensional space, not necessarily a vector subspace. It is going to be a k-dimensional subspace in the feature space. Right? X is maybe in some k-dimensional manifold. Or when you look at P of X, most of the variation in some k-dimensional subspace. So now again, let's assume that we are operating in the feature space. If we were to do PCA, standard PCA on the feature space, what would we require? So for simplicity, let's assume that the feature space is finite dimensional. Okay. Then what I can do is look at the matrix Y, which is Px1 up to Pxn. So you stack all of the feature vectors as a big data matrix. This is a capital D by n matrix, where this capital D is the dimension of the feature space. So PCA would amount to finding the top k eigenvectors of YY transpose. I can't really do this, right? Because I don't want to operate in the feature space. In general, operating in the feature space is hard. It could be, I mean, in principle, the feature space could also be infinite dimension. Or, I mean, the whole point of dimensionality reduction is to reduce complexity, reduce space. Right? So if I'm operating in the feature space, which is a very high dimensional subspace, high dimensional vector space, then that beats the purpose. So I want to find the top k eigenvectors of y transpose, but as we see, we don't need to find the k top vectors of y transpose. There's a much nicer representation that is possible. In the end, I just want to, I want a nicer representation for x, right? So, for instance, suppose that all of my data points are so my suppose all of the data points look like this. So d is equal to 2, but in some sense this lies in a one-dimensional space, whatever that space may be. So all of the, let's say that all of the points are all of them approximately lie on a circle. You can think of this circle as a one-dimensional space, or maybe all of them lie on a parabola. If I try to do just normal PCA, then it would tell me that like all of the data lies in RD. I can't really so in this particular case, there's no single direction along which more of the variation is present. It's because it looks the same in all possible directions. But as we can see, it's this scenario is very different from the scenario where the points are, let's say, uniformly random. It's scattered throughout space. That's not the case, right? So if I were to, let's say, map these points into a higher dimensional feature space. So for instance, let's take this case where the points lie on this circle. If suppose that I were to map this to R3, right? I look at the following mapping: x1, x2, comma. Okay, yes, maybe not. Right? Let me put that example aside. But so maybe it's possible to map this into a higher dimensional space such that all of these points lie along a line in that particular higher dimensional space. Okay. Again, how do you find this feature mapping? That could be a complicated problem, right? But whatever it is, I want to do PCA over this higher dimensional feature space. Okay. So I want to find the top k eigenvectors of y transpose. But that in general may not be possible. So let's assume that the matrix, the data matrix in the feature space, has the following singular value decomposition. Right? So I can write y as some u lambda v transpose. So what is y transpose? This is just equal to u lambda square u transpose. Correct? So effectively what I want to know is what are the top k eigenvectors here in the matrix. Correct? So I want to find the u1 through uk corresponding to the k largest eigenvalues or the k largest absolute singular values in lambda. All right. But on the other hand, what is y transpose y equal to? Correct. So it is certainly V lambda square V transpose, that is for sure. But what exactly is Y transpose Y in terms of the data matrix? Yep, so it's basically the entries are essentially the inner product between phi xi and phi. The ijth entry of Y transpose Y is the inner product between phi xi and phi xj, which is the kernel matrix, right? So this is the kernel matrix K. Okay, so that is pretty good. Now let's see. So essentially, the eigenvectors corresponding to the k largest eigenvalues of YY transpose, there's a one-to-one mapping between those and the eigenvectors corresponding to the k largest eigenvalues of Y transpose Y, because both of these have the same set of eigenvalues, right? Of course, the same set of non-zero eigenvalues, because the dimensions of YY transpose and the dimensions of YY transpose Y could be different. In general, this is going to be different. So, in fact, Y transpose Y is going to have, in general, going to have more, again, depending on how many data points you have. One of these is going to have more eigenvalues than the other, and those are going to be 0. Right? Okay. So in other words, to find the k largest eigenvalues of Y transpose, I can just find the k largest eigenvalues of K. Right? Because YY transpose and the matrix K have the same eigenvalues. Or top, let's say L eigenvalues. Let's say that the top L eigenvalues are lambda 1 through lambda L. The corresponding UIs, that is the vectors that we're really interested in finding, are U1 through UL, which we don't know how to find yet, but we can compute V1 through VL, which are the eigenvectors of the corresponding eigenvectors in Y transpose Y. Right? Because Y transpose Y is just K. So I just do an eigen decomposition of K. Okay. Now, in general, what's the purpose of dimensionality reduction? Given a new vector, I want to be able to find the projection onto this lower dimensional subspace. Right? So what is that projection? It is just going to be, call it Y transpose U. Right? Let's say that I want to find, going to be U times Y. Right? That, I'm sorry, not U times Y, it's going to be U transpose times Y. So in other words, I need to be able to compute UI transpose Y for each, for I equal to 1, 2, 3 up to N. All right? Which is just an inner product between ui and y. All right. Um, but now I make use of the following fact. So I have, let's say, C, which is y transpose. Let me write in the following way. So I know that y is u lambda v transpose, right? Um, what is u equal to? Just from this, I know y. Okay, let's assume that I know y, but no, we don't really know y, but we sort of play around with this y. I can compute lambda because I can find lambda from y transpose y from the using the kernel matrix, and I can find v. All right. So those are our knowns. Let's treat u as the unknown. Still don't know y, but let's see what we can do. So this is equal to y times v times lambda minus 1. Assuming, of course, that lambda is inverted. So what is perhaps more important is that ui is simply going to be y times vi divided by lambda. So given an entirely new vector y, right? So this corresponds to, let's say, some phi x. Right? So y is equal to phi x. I want to find u transpose y. This is equal to, let's say, to find this, I need to find, say, ui transpose y, which is ui transpose phi x, which is nothing but vi transpose y transpose px divided by lambda I. Right? It's a long sequence of steps, but effectively all that's important for now is that if I want to find the corresponding PCA representation of a new point y, then that amounts to finding ui transpose y for I equal to 1, 2, 3 up to L, and that amounts to finding ui transpose phi x or vi transpose y transpose phi x. Now lambda I is known to us. Vi is just corresponds to the ith largest eigenvector of k. What is y transpose phi x? How do you find? So what is y? It's just phi x, right? So this is just phi x1 transpose phi x2 transpose up to phi xn transpose. This times phi x, right? This is again just a bunch of inner products which you can evaluate, right? Just using the kernel K. So this whole thing just happens to be K of x1 x up to K of xn. The bottom line is that, again, even though you're trying to find a representation in some lower dimensional non-linear space, you can still do it without too much computational complexity. Again, the computational complexity will scale with the number of data points that can't be helped, but it only scales with the dimension of the domain space and not the feature space. Again, this was just a high-level overview of what kernel PCA is and what the main ideas are. There's still a lot of low-level improvements that you can do to improve the computational complexity. How you choose the kernel is, of course, another story. Maybe I just stop here, the natural stopping point. Any questions? Which you pick a particular kernel. Again, yeah, again, if of our choice. Why do you need kernel PCA? Exactly in for to take care of examples that look something like this, right? Where a lot of the data is present in some very low dimensional manifold or a very low dimensional surface of RD, where standard PCA doesn't work. Standard PCA is not able to find any small subspace, low dimensional subspace where most of the variation is present. Correct. So we're but then still you're doing all of the computations in a lower dimensional space. You can't, right? Because you can't do operations, you can't do linear operations and get away with it. The nice feature about all of this is you're just doing linear algebra. That's it. Even though you're dealing with non-linear spaces, all of the operations you're doing are essentially matrix operations. SVD, in fact, just eigen decomposition and matrix multiplication, nothing more. This non-linearity is being introduced by the K, but you don't have to worry about this non-linearity. Okay, so let's stop here.